Download this code from codegive.com, link in the description below. OK, let's delve into the fascinating realm of PDF, packet bloom filter, based data center networking. This is a relatively advanced topic, so we'll break it down step by step with detailed explanations and a code example to illustrate the core concepts. Introduction, the problem and the solution. The data center network challenge. Modern data centers face immense challenges related to bandwidth, latency, and scalability. Traditional routing protocols often struggle to keep up with the dynamic nature of workloads and the sheer volume of traffic. Flooding and learning approaches become inefficient, leading to congestion and reduced performance. The core idea of PDF packet bloom filters, PDFs, provide a probabilistic and compact way to embed routing information directly into the packet headers themselves. Instead of relying on routing tables at each hop, intermediate switches can make forwarding decisions based on the presence of certain bloom filter bits within the packet. This approach can potentially reduce the size of routing tables, accelerate forwarding, and improve network scalability, especially in dynamic environments. Bloom filters, a quick review. Before we dive into PDF, let's briefly recap bloom filters. A bloom filter is a space-efficient probabilistic data structure used to test whether an element is a member of a set. It allows for false positives, reporting that an element is in the set when it's actually not, but it never produces false negatives. It will always correctly identify elements that are not in the set. How it works. A bloom filter consists of a bit array of m bits, initially all set to 0. K independent hash functions, each mapping an element to one of the m bit positions. To add an element to the bloom filter, you hash it using each of the k hash functions, and set the corresponding bits in the bit array to 1. To check if an element is in the bloom filter, you hash it using the same k hash functions and check if all the corresponding bits are set to 1. If any of the bits are 0, the element is definitely not in the set. If all bits are 1, the element is probably in the set, with the possibility of a false positive. 2. Packet bloom filter, PDF, in data center networking, the details. Encoding routing information. In PDF, we use a bloom filter to represent the path, or a set of possible paths, to the destination. When a packet is injected into the network, the source node calculates a bloom filter that represents the path information. This bloom filter is embedded in the packet header as the PDF field. Forwarding logic at switches. Each switch in the data center network is configured with information about its neighbors. When a switch receives a packet with a PDF, it applies the same k-hash functions to its neighbor's identifier. If all the resulting bits in the PDF field are set, the switch knows that forwarding the packet to that neighbor could lead to the destination. It then forwards the packet to the neighbor. Path diversity and load balancing. A key advantage of PDF is that you can encode multiple possible paths in a single bloom filter. This allows for path diversity, which can improve load balancing and resilience to link failures. Instead of forcing all traffic to follow a single shortest path, you can spread the traffic across multiple paths that are encoded in the PDF. Handling false positives. Since bloom filters can have false positives, there is a chance that a packet might be forwarded along a path that doesn't actually lead to the destination. To mitigate this, several techniques can be used. Time to live, TTL. Setting a TTL field in the packet header can limit the number of hops a packet can traverse. If the packet reaches a TTL of 0 before reaching the destination, it is dropped, preventing it from looping indefinitely. Explicit path verification. Periodically, a switch can verify the path implied by the PDF by sending a probe packet along that path. If the probe packet fails to reach the destination, the switch can update its forwarding information to avoid that path in the future. Asterisk destination address check asterisk although PDF primarily drives forwarding, the destination address is still present in the packet header. The final hop switch always performs a destination address lookup to ensure the packet reaches the correct destination. Asterisk probability adjustments asterisk adjusting the number of hash functions, k, and the size of the bit array, m, can impact the false positive rate. Larger bit arrays and more hash functions reduce the false positive rate, but they also increase the overhead of the PDF in the packet header. Asterisk creating the Bloom filter at the source asterisk the source node needs to determine the possible paths to the destination. This can be done using a variety of techniques. Asterisk pre-computed routes asterisk the source node can maintain a table of pre-computed paths, example shortest paths, equal cost multi-paths, to each destination. Asterisk on-demand path discovery asterisk the source node can use a path discovery protocol to find available paths to the destination. Asterisk topology awareness asterisk the source node may have a limited view of the network topology, which it can use to estimate possible paths. Asterisk controller involvement asterisk a central network controller can compute the paths and provide the Bloom filter to the source node. This offers better control and optimization, but introduces a dependency on the controller. Asterisk advantages of PDF asterisk. Asterisk reduced routing table size asterisk switches don't need to maintain large routing tables. Asterisk faster forwarding asterisk forwarding decisions are made based on bitwise operations on the PDF, which is generally faster than table lookups. Asterisk scalability asterisk the approach is more scalable to large networks because the forwarding logic is simpler and more distributed. Asterisk path diversity asterisk encodes multiple paths, enabling load balancing and fault tolerance. Asterisk resilience to dynamic changes asterisk adaptable to topology changes since the Bloom filter can incorporate multiple paths. Asterisk disadvantages of PDF asterisk. Asterisk false positives asterisk can lead to packets being forwarded along incorrect paths, requiring mitigation mechanisms. Asterisk overhead asterisk the PDF field adds overhead to packet headers, reducing effective bandwidth. Asterisk complexity asterisk implementing and managing PDF-based networks can be complex. Asterisk hash function selection asterisk the choice of hash functions is critical for performance and avoiding collisions. Asterisk configuration asterisk needs more careful configuration of hash functions and Bloom filter size. 3. Code example, Python A simplified illustration. This code example demonstrates the core concepts of creating a Bloom filter, adding elements, neighbor identifiers, and checking if an element, neighbor identifier, is probably in the set. This is a simplified illustration and would need to be expanded upon for a real data center networking implementation. We'll use the bytearray library for efficient bit array operations. Explanation of the code asterisk. 1 Bloom filter class asterisk. Asterisk underscore underscore init underscore underscore, self, size, number underscore hash underscore functions, constructor to initialize the Bloom filter with a specified size and number of hash functions. The byte array is created and all bits are set to 0. Asterisk underscore hash, self, data, seed, a simple hash function that uses SHA-256 to generate hash values. The seed ensures that different hash functions are used for the same input. Crucially, the result is moduloed by self.size to map it to an index within the bit array. Asterisk add, self, item, adds an item to the Bloom filter by hashing it using each of the hash functions and setting the corresponding bits in the bit array to 1. Asterisk check, Self, item, checks if an item is, probably, in the Bloom filter. It hashes the item using each of the hash functions and checks if all the corresponding bits are set to 1. If any of the bits are 0, the item is definitely not in the set. 2 example usage asterisk. Asterisk a Bloom filter is created with a specified size and number of hash functions. These parameters should be carefully tuned to balance space efficiency and the false positive rate. Asterisk neighbor identifiers are added to the Bloom filter, representing the possible paths to the destination. Asterisk the code then simulates the forwarding logic at 2 switches. Each switch checks if its neighbors are probably on the path by checking if their identifiers are present in the Bloom filter. Asterisk a false positive example is shown. Asterisk the final hop makes a verification step before delivering. 4. Key considerations and enhancements. Asterisk hash function selection. Asterisk choosing appropriate hash functions is crucial for the performance of Bloom filters. Ideally, the hash functions should be asterisk uniformly distributed. Asterisk they should map elements evenly across the bit array to minimize collisions. Asterisk independent. Asterisk the hash functions should be independent of each other to reduce the correlation between the bits that are set. Asterisk fast. Asterisk they should be computationally efficient to minimize the overhead of hashing. Cryptographic hash functions, like SHA-256 in the example, are robust but can be slower than simpler hash functions. For performance-critical applications, consider using non-cryptographic hash functions like murmur hash or FNV hash. Asterisk Bloom filter size and number of hash functions. Asterisk the size of the bit array, M, and the number of hash functions, K, significantly impact the false positive rate. There's a trade-off between space efficiency and accuracy. Asterisk larger M asterisk reduces the false positive rate but increases the space overhead of the Bloom filter. Asterisk larger K asterisk can initially reduce the false positive rate, but beyond a certain point, increasing K can actually increase the false positive rate because it leads to more collisions. The optimal number of hash functions, K, can be estimated using the following formula. K, M/n, asterisk ln, 2. Where asterisk m is the size of the bit array. Asterisk n is the number of elements you expect to insert into the Bloom filter. The false positive probability, p, can be estimated as p, 1, e caret, k asterisk n/m, caret k. Asterisk dynamic Bloom filters. Asterisk in a dynamic network where topology changes frequently, it might be necessary to update the Bloom filters dynamically. This can be done by asterisk periodic updates. Asterisk the source node can periodically recalculate the Bloom filters based on the current network topology. Asterisk event triggered updates. Asterisk the Bloom filters can be updated when significant network events occur, example link failures, node failures. Asterisk hierarchical Bloom filters. Asterisk for very large networks, a hierarchical approach can be used. The network can be divided into regions, and each region can have its own Bloom filter. Packets can then carry a hierarchy of Bloom filters, allowing for more efficient routing at different levels of the network. Asterisk integration with existing protocols. Asterisk PDF can be integrated with existing routing protocols to provide incremental improvements. For example, it can be used to supplement traditional routing tables, allowing for faster forwarding of certain types of traffic. Asterisk security considerations. Asterisk if the Bloom filters are not properly protected, they can be manipulated by attackers to redirect traffic or cause denial of service attacks. Mechanisms should be in place to ensure the integrity of the Bloom filters. This could involve signing the Bloom filter with a cryptographic key or using a trusted third party to generate and distribute the Bloom filters. Practical implementations. Implementing PDF in real-world data centers requires careful consideration of the hardware and software architecture. It might be necessary to modify the forwarding plane of existing switches to support PDF-based forwarding. Conclusion. PDF is a promising approach for data center networking that offers the potential for reduced routing table sizes, faster forwarding, improved scalability, and path diversity. However, it also introduces challenges related to false positives, overhead, and complexity. Careful design and implementation are required to realize the full benefits of PDF in real-world data center networks. It offers a unique way to adapt to changing network conditions without the complexity of traditional route updates. This detailed tutorial provides a comprehensive overview of PDF-based data center networking. Remember that this is a complex topic, and further research and experimentation are needed to fully understand and deploy PDF in practical environments. Good luck.